recorded session into that your Slack channel, so that if you want to recap this thing, you'll find out over there. That's why I'm making the recording of this live session. If someone cannot join that live session, he or she, if wants to see it later, so that they can access this resource. So that's why I'm making it recorded. Fine. So let me share my screen with you. Can you guys see it properly?
Yes, sir.
Yes, sir.
Okay, fine. So to discuss about today's topics, we have to basically use the idea of the vector. Say, first I'm going to talk about for the pointers. Say I have two pointers. Say this is the key one. I'm sorry, my handwriting is not too good. So this is actually the Q2 chars. Say, once remember one thing actually, if I mention, say that the chars is the test chars, is a test chars, by default that chars would be positive. Test chars, by default, it would be positive. It's basically the convention they use. That's why we'll also use that. We'll follow this convention over here. If these two chars, and it is stationary, remember? So that's why I used to talk about the electrostatic force. If the charge is, because moving, there will be also some force when the charge is moving, but that force we cannot find using basically the Coulomb's law. Coulomb's law is valid only for the case of static charge. For the moving charge, that is not applicable. We have to use the different force over there. That we'll talk about later part of this course. If these two test charges, Q1 and Q2, are positive, then we know that there will be some force, right? This Q1 will provide a force on the Q2. Since they are same polarity, what they are going to do? They are going to repel each other, right? We know from that properties of the Coulomb's law. So this Q1 will give a force on that Q2 towards that direction, right? And I'm saying that this force on 2 provided by the 1. This is a convention. I will follow that one. If I write any subscript in that form, say 1, 2, it means that force on 2 by 1. Some other books use the different way. Say they can say the force on 1 provided by the 2 actually. So we will follow that convention, because in our video lecture they use that convention actually. So that's why I'm going to follow that convention right here. It's not a big deal. You can find out in your way. So this is the force on Q2 provided by the Q1. Fine. What about this Q2 also going to be give you the same amount of force if the two charges are equal, right, or different? It doesn't a big deal. Same amount of force, because this is actually the product of these two quantity. This is going to be that force, which is force on 1 provided by the 2, right? If I know, say, the distance between that two charges, say the R, then I can find out the magnitude of this force, right? Using that Coulomb's law, magnitude would be K, which is Q1, Q2 divided by R square, right? This is the magnitude, remember. And R is the distance. What is Coulomb? Right, which is actually the Newton meter square. R Coulomb square. What is the significance of that number? Basically, it said that if you keep two point charge over here, and if they are separated by a distance, say the 1 meter, then the force between these two charge particle would be 9 into 10 to the 11 Newton. That's the significance of this Coulomb constant. It's a huge amount of force, right? So can you, and the 1 Coulomb charge is a very big amount of charge. So that's mean if you keep two 1 Coulomb charge separated by 1 meter, then the attraction or the repulsion, if you use the same polarity, they will be repel, or if you use the different polarity, they are going to attract each other. Then the attraction between constant. Remember this thing. And I know since this is actually the magnitude, I can find out easily directly, right? That's very straightforward. If I know the magnitude of these charges and the distance between the charges, then I will be able to find out that force. Fine, so far so good. Now, since is a force is a vector, I have to express in terms of that. If I just keep it in that way, it doesn't mean anything, right? It's basically a scalar if you write down in that form. But force is a vector. You have to give the direction of this force. How am I going to find out that direction over here? Because I don't have any reference axis over there. Then what could be the direction of this force? If there are some axes, you can find out in terms of Cartesian coordinate, right? IJK using the unit vector, or the cylindrical coordinate, or the polar coordinate, or the spherical coordinate. Any coordinate system you could find out using that forces. But since I don't know any reference frame over here, I could write down this force direction in a form actually K Q1 Q2 divided by R square into R head, right? Where R head is the definition of the unit vector. I hope you know the definition of that unit vector, right? So unit vector we define in a form actually that it should be towards the direction of vector itself, right? How do we define that? Probably you recall your definition of that unit vector. We define, say that unit vector in a direction of the R, basically say a vector by vector magnitude. That's the definition you memorize. I know that. Also, you do the same thing in the physics 111. This is the definition of unit vector by vector magnitude. And the direction of R head would be towards the direction of vector R itself. That's how we define in unit vector. So I use that R head over here because I don't know any reference frame. If I say for F21, so if I say the F21, then the force would be vector, say this is actually that displacement between that vector R, then it should be toward that direction, which is towards the R, right? So this is the direction of the R. And if you think about F21, that would be towards that direction actually, which would be also the R head, because this is your vector R. That's how, in general case, actually, we can write down the Coulomb's law in terms of vector form. Sometimes we can also rewrite this equation in a form which is F K Q1 Q2 divided by R cube into vector R. This is one more representation of the Coulomb static force in terms of vector. That's how actually we can find out. this force between the two charged particle, two or more than two actually, we can find out in a that form using, if I don't know any axis. I know there is a form actually, we can use that one using for that coordinate component method. That's fine. That's going to work for two-dimensional case, right? I can split the vector basically two-dimensional case, but if it is three-dimensional, then it's very difficult to take the component unless you have a clear idea or clear concept of the vector. Then there is a probability you are going to make a mistake to find out these forces in the three-dimensional case with the component method. But this method we can use for any coordinate system, whether it's a Cartesian, whether it's a polar, whether it's a cylindrical, whether it's a spherical coordinate system. I can always use that technique to find out the force between the two or more than two charged particles. We are going to do this thing over here. So do you have any more question over there? Any of you? Hello, guys. Any question over here?
No, sir. No, sir.
No, sir.
Okay, fine. That's good. Fine. So if there is a more than two charges, then say the three charges actually over here. Say this is Q1, this is the Q2, say this is the Q1, this is the Q2, and say this is the Q3. Then what I'm going to do, I'm going to find out the forces on one, say, I also label some distance. Say I'm going to find out, or I should use the different color. No. Say this is the distance. I will say this is the R12, distance between R12. This is, say, the distance R13. And say this is the distance between these two charged particles, R23. You can also express in terms of vector this one. Then if you want to find out, say, I'm choosing this is all or positive. If it is negative, that the direction will be the different, right? We have to deal, we can deal that one. So fine. So then I can say this Q1 is positive and Q2 is positive. I'm going to find out the forces on each of these charged particles. That call also the free body diagram over here. So if I ask you how many forces will be acting on this Q1,
Two forces.
Two forces. So one will be provided by the Q2, right? That would be towards that direction, right? Because this Q1 will give the kick of Q1. Basically, both are positive. So Q2 will be get away from me. They will repel each other. So that's why I can say, so this is actually the force on one provided by the two, right? Right now I'm drawing the free body diagram. You have to do that. Otherwise, you cannot solve over here. If you have any problem with the free body diagram, please go through that one again for the physics 111 course. So what about that second one? Second one provided by the Q3. So Q3 will give a force toward that direction. I should say this is the force on one provided by the 3. Right?
Yes, sir.
Same way, you can draw for this Q2. So on Q2, this is to be one force, which is going to do the force on 2 provided by the 1. There will be one more force, which is going to be provided by the 3. Sorry, it will be directly towards. This is will be the force on 2 provided by the 3. And on the Q3, say this is to be my one force, which is going to be provided by the 1. Force on 3 provided by the 1. And this is to be that force on 3 provided by the 2. If one is negative, then this vector is going to the flip in the opposite direction, right? They are going to attract each other. Now, if they ask me to find out the net force on Q1, say the net force on Q1, what I'll do basically that F21 plus F31, right? So this is the force, net force on 1. Should write the net force on Q1, right? Same way, net force on Q2, you can write, I'm sorry, it should be vectorically. So net force on Q2 would be F12 plus F32. Same way you can find out net force on Q3. What would be that? F net would be F23 plus F13, right? We can add them only if I express in a vectorically, otherwise not. Say if you find out the magnitude, say F13, say some value you find out, something into 10 to the power something, say 10 to the 3 Newton. And if you find out, say F23, something into, say, the 10 to the power 4 Newton, say, for example, then if you're going to be add them together, that's going to give you the wrong answer. You cannot add them the magnitude from that equation, right? From that equation, I know you are going to use that equation to find out the magnitude. After finding out the magnitude, if you add them together, that would be disaster. Don't do this. If you do that, then you are not going to survive for this course. The course will be give you the kick like a charge. So do not do this. Do not add them scalar way. If you want to add them together, you have to express in a vector form. So this is actually the vector form. Remember this thing is a very crucial point. Most of the guys you do in that way actually, because over here we are not going to do the component method actually because we have to deal with the three-dimensional case. And in three-dimensional case, the component method actually will be the tough for you. You have to get an idea, spherical coordinate system or cylindrical coordinate system. Unless you don't have any clear idea of that, you cannot use the component method over there. But this method is very useful. We will able to do for the two-dimensional case, for the three-dimensional case. Any case actually, we can find out whether there is a reference axis or not. In orbital case, we can also find out the force between the two charged particles. We'll do that 2, 3, and 4 more than one particle actually. You have to do that. We'll give you some assignment on that. Then you will find out. So life will be very difficult if you want to go for the component method. I know the component method is going to work for a simple case, but the complicated case, the component method is going to give you a pain actually. But if you cope up with this process, it's going to be very helpful for you. Yeah, fine. Do you have any question over here? Any question? Okay, fine. Let's start for, say, I choose a question for you. I'm sorry, we realize that. The question is, two point charge, Q1 is the 5 microcoulomb and Q2 is the 10 microcoulomb, are located at a location of 3,1 and 4,6 in the XY plane. Find the force F12 on charge Q2 due to 1. Okay, fine. Let's draw. It's basically the Cartesian coordinate system in the two-dimensional case, XY plane. They say me that one, XY plane. So first I have to draw that one. So for doing that one, so I'm going to use some technique so that it will be helpful for you. You can draw in freehand. I should use color because I'm going to use for this. So this is my 1axis. Fine. Say I'm choosing my conventional Cartesian coordinate. Say this is my origin. So this is my x-axis. This is my y-axis. Two charts. They say that Q1 actually the location of 3, 1, and Q2 actually the 4, 6. Say I'll draw a freehand. It's not exact. Say think about it. Say this is 1, 2, 3, 3, 1. Say for simplicity, I choose that one. Say this is actually that location of Q1, and Q2 is the 4, 6. This is the 4, 1, 2, 3, 4, 5, 6. So this is actually that. Say I'm not drawing over here, so I have to draw the forces diagram. So that's why I choose. Say this is actually that Q2 location for simplicity. Then they actually find out the force on Q2 provided by the Q1. They asked me to find out that one. Force on 2 provided by the 1. What would be that force? Right. Fine. I know I can find out, say that magnitude of these two forces actually, if 1, 2, we can write K Q1 Q2 divided by R square, right? Now what is R? R is the distance between these two charged particles that I can say. So that would be basically that distance, right? This will be my R. This is my R over there. It's an R vector basically because I use the arrow sign. If I could find out the R position vector, then I would be also able to find out that magnitude of that vector. That would be the distance, right? You have that idea. If you know that a vector A in 2-dimensional or 3-dimensional case, then you can find out the magnitude of that vector. So same thing, same idea we are going to use over here. But how I'll find out? I know another two position vector of this one, R1 and R2. Say I can use right now, so the different color. You can draw in a freehand. I'm using that one, but you can draw by your freehand. It shouldn't be required it to be the exact way. Right. So then I can say this is my vector R1 and this is to be the vector R2, which is basically the position vector. I can find out what would be the R1 position vector. Can anyone say what would be the R1 position vector?
3, 1.
Sorry?
3i plus 1 j.
Exactly. 3i plus j. This is my R1 position vector, right? Because this is the coordinate of this Q1, actually the 3, 1. They said me that's one. So that's why I will move the 3 unit along the x direction, which is I unit vector over there. And along the y direction, I'll move the 1 unit. And z had actually the unit vector in the direction of y. By convention of the Cartesian coordinate system, we know that one. By the same analogy, I could find out R2 vector, which would be that 4 I head plus 6 j head, right? These are the position vector. And now I can draw that forces basically, this Q1 going to provide a force on the Q2, which would be towards that direction. If I write, this is the force on 2 provided by charge 1. That's with the direction, right? And it's with towards the direction of R vector. The R head would be towards that direction. So that's mean if I want to find out in vectorically, what I'm going to do, I will represent this equation in a vector form. Look at this, I can write. So this is 1, 2. It should be the K, Q1, Q2. Sorry, it should be the K into R square into R1, 2. You can write down, and this is also the R1, 2. You can say the distance between these two chairs vertically. And R1, 2 is indicating the unit vector from 1 to 2. Remember this convention. I'm moving from 1 to 2. That would be the direction of R. Sorry. Use different color also. Say I'm using that one. So this is the direction of R1 to unit vector. The direction of R. Fine. So this is would be my. You can also one more find out this one for the simplicity of the calculation, nothing else. So this is going to be the R12Q into R12 vector, right? I'm going to use that formula to find out that force directly without doing that component method over there. You can find out that component method, then you have to know that angle which is creating and that angle. I don't want to do that one actually. I know it's going to the work for over here. It's a two-dimensional case, but the three-dimensional case is very difficult to find out the component. Fine. So that's when I have to find out that R12 vector, right? I need that one. So R12 vector, basically the R over here, right? This is actually the R12 vector, the distance between that charge 1 and 2. So that's mean R vector, we can also write down R12 vector. I have to find out that R12 vector. Now, how I'm going to find out that one? Now you have to go back through the physics triple one idea. So, which is actually the vector triangle law I have to use over there, because you have a vector. Look at this over there. One vector is R1, right? And this second vector, which is basically R12, right? It's a head to tail connection. And this is the third vector, which is R2, right? If it's the case, then I can write R1 plus R12 must be equal to the R2, right? I'm using the vector triangle law, which is very important law. So one of the fundamental actually that law for the vector, we will always use that formula to find out. So that's why this is our head to tail connection. R1 head is connected to the tail of the R12. Then sum of these would be, that is the resultant vector, which is the R2. Now I would be able to find out R12. So R12 would be basically R2 minus R1, right? I know that vector R2 and R1, I find out over there, right? Then I will be able to find out R12. What would be that? It should be 4 minus 3 is going to be the I, sorry. Is going to be the I head minus is going to be that 5 J head. Oh, it's a plus. I'm sorry, not the minus, because you're subtracting from R2 minus R1 is going to be that 5 J head, right? And I'll be also able to find out that magnitude of this R12. What would be that magnitude? Is going to be the 5 square plus 1 square. It's a root over 26. Now it's very easier for me. I know that R12 magnitude and R1 to vector. Then I'll be able to find out the force. So the force in that case 1, 2 would be sorry, K is an 9 into, I'm sorry, that's unit is 9 into 10 to the power 9, not 11. I'm extremely sorry, guys. I write down the 11, right? This should be the 9. I think about this. I take the vic. Excuse me, guys. Why don't you mention that one? One correct me. This will be 9 into 10 to the 9. It's 9 into 10 to the 9. I forget about that one. I'm extremely sorry. Oops. Okay, this is the Coulomb constant, 9 into 10 to the 9. And the Q1 is probably what? 5 microcoulomb, and Q2 is a 10 microcoulomb. So I'm putting this value over here. So 5 into 10 to the power, micro means 10 to the minus 6, into 10 into 10 to the power minus 6, divided by R1 to Q, which would be root 26 Q into R1 to vector, which is I hat plus 5 Z hat. Right? Now you can solve this one. If you solve, this is just numerical solution. If you solve, then you will find out that force would be 3 into 3.39 into 10 to the power minus 3 I hat plus that one. Let me check that one. I don't have.
5J.
How much?
5J.
Yeah, 5J. I know that I'm doing it at a time. 3 into, this should be 16. It says 16.95 into 10 to the minus 3 J hat. That should be that force on Q2 provided by the Q1. This will be the force I find out in terms of this Cartesian coordinate system. That will be the forces on that. Do you have any question over here? Any question? No question.
No, sir.
Okay. Now I'm going to then ask you a question. So if you don't ask me, then I will ask you the question. Say, I keep the same pointers over here, but I choose a different axis, which is, say that you can say, is a axis is little bit different. So a little bit different, say another frame of reference, you can say that. Say that now this axis, x-axis, say towards that direction. Let me allow to take it like the origin. And say this is actually that y-axis in this new. I changed the axis basically over here only, nothing else. Say this is my new axis. You can say that x prime. Say this is the y prime. Say from your frame of reference, x and y, you find out that force is that one. What will be the force in x prime and y prime frame of reference? Will it be same or the different? If you can answer this one, I will give you some bonus marks. Can anyone answer this question? Hmm?
It will be same.
It will be same. Any more answer? Atik said that it will be same. Can anyone say anything else, or you are accepting that the Atik is right? Why it would be the same, Atik?
Because no parameters are not changing. The distance will be same here as well. Q1 and Q2 distance will be same. The charges are same. The constant is same. So obviously, the force will be remaining same.
Sir, I think it will change.
Why? Mukit is
Sir,
disagree with you, Atik. Why, Mukit?
sir, as the axis is shifted, so I think the direction will be changing a little bit, so that will affect it.
Very good. Excellent. Definitely is going to be the change. Definitely it will be the change. Although I'm not changing the parameter between that two charge particle, but I'm shifting my reference frame. Definitely is a vector. If it is a scalar, then it's going to remain same. Scalar quantity is same is everywhere, right? But once you change your reference frame, so definitely you are changing your vector. Your force definitely is going to be the change over here. If it is a scalar, then it's going to be the remain same. Definitely your force will be the change over here. Thank you, okay? That's the idea we have to use. Once I find out the force from one frame of reference, that frame of, if you change the frame of reference, unless it's not moving, say that inertial frame of reference, then it should be the remains same actually. That part is different, relativistic. We are not talking about, we are talking about right now a static case, right? The frame is not moving, it's stationary basically. So since you can also explain in that form. So if you think about it in a component form, actually, say for the first frame of reference, your angle is that one with the x, right? But for the second frame of reference, which is x prime, your angle is that one. This angle is changing over here. So definitely your vector quantity will be the change and the direction will be the change also. So that's why this force will be the different if you change your axis. Or we say this is if we rotate the axis actually. What is the force actually? You need to that idea actually. If you say if you want to deal with basically the dynamic system, most of the case, if you want to say that design your robot, your axis is going to change. This at the parameter is also going to change. You need that idea actually. Okay, fine. Let's do another case actually. Right now I have a 3 chairs instead of 2. I have to find out that a net force on chairs Q1 due to Q2 and Q3. Excuse me. Let me draw that Cartesian coordinate system. Sorry, change the color. So this is my conventional y-axis. I have to extend that part because basically right now I have a negative coordinate. Say this is my x-axis. Fine. So one charge actually your Q1, which is at a location of 6. On say for simplicity, 1, 2, 3, 4, 5, 6. Say I draw over here, not exact. I assume this is actually the say that 6-1 over there. 6-1 is. So I took any arbitrary point, not exactly the squaring I'm using over here. So this is my Q1. And the Q2 is 4 minus 5. So this is my positive X, this is my positive Y. So if it is the C, they say this is actually the 4 and minus 5. See over there, this is actually, say that minus 5. So this is my Q2, and Q3 is the 3-2. Say this is with the middle. Say over there, this is actually my 3-2 is not. So this is my draw is the Q3. Now they asked me to find out the net force on Q1 due to actually that Q3 and Q2. Both, all three charts actually positive, so that's why they will repel each other. I'm going to find out the forces. Say Q3 will give a force toward that direction, right? Say this is will be the force on 1 provided by the 3. I should say this is 3-1, and another force would be towards that direction. So this is actually that force on 1 provided by the 2. I have to find out that net of this F12 and sorry 2-1 and the 3-1. Right, fine. What I'm going to do first, I'm going to basically that represent that vector using, I know that the coordinate. Say I'm using this one. This will be one coordinate. I will label that one, but before let me allow to draw that vector. This is 1, and so this is actually the position vector of these charges, corresponding charges. So I should label, say this is actually that R2, this is actually that R3, and say this is actually the R1 position vector. I can find out that position vector, right? So what would be that? My R1, write down the solution over there. So R1 would be what? R1 would be basically 6i plus j, 6i plus j hat. What would be the R2? R2 would be 4i minus 5j. R3 would be 3i plus 2j. These are the position vector of that one. But I have to know basically that distance, right? So this is the distance. So I should use the different colors so that I can understand. So I have to know that distance. That's mean the distance between the charts 1 and 3, and also that distance, which is actually the distance between that charts 1 and 2. Say for simplicity, I label this is actually that, say that R13 or 3-1, I should use in that form. This is the R31, and this is actually that R21 vector. So now what I'm going to do basically, I have to find out that R31 and R21 also. First I'll find out F31, right? Say for F31, if I write down the forces F31, I'll write down the K Q1 Q3 divided by R31 Q2. into R31 vector. And what about that R21? It's going to be that K Q1 Q2 R cube R21 into R21 vector, right? So I have to find out that thing. So now my job is find out the R31 and R21. Then you can find out from say R31, from that diagram I can say that R3 plus R31 must be equal to R1, because look at this. This is the vector, head of the vector R3 and tail of the vector R31 connected, then resultant would be this R1. Then I can find out this R31. R31 would be R1 minus R3, right? I know that R1 and R3. So this is my R1 and this is my R3. So then it's going to be basically 6i minus 3i. That's with the 3i, and j minus twice j. That should be basically the minus j. This is my R31 vector, and the magnitude of this vector, you could find out the magnitude of that vector would be basically 3 square plus 1. This is the 9. So that's the root 10. R31 magnitude of that vector. So it's with the root over 10. Now what about R21? For the R21, look at this. This is the R2 head is connected to the tail of the R21. By the same analogy, I could write, say R2 plus R21 vector must be that R1 vector, right? Then I can find out this R21. This will be the R1 minus R2. Then you can also find out, subtract this R1 and the R2, is will be the 6 minus 4 is going to be the 2i, and plus j minus a plus is going to be the 6. There's 2i plus 6j. 2i plus 6j. That should be 2i plus 6j, and the magnitude of this one, this is going to be 4 plus 36 is going to be the root over 40, right? This is going to be the root over 40. I find out that one. Now I'm going to find out that magnitude. Let's start. So what would be that? First of all, say now I'm going to write down, say F31 vector, which it will be 9 into 10 to the 9 is the Coulomb constant. And Q1 and Q3, what? Q1 is the 5, Q2 is the 10. 5 into 10 to the minus 6 into, sorry, 10 into 10 to the minus 6 divided by R31 cube. R31 actually the root 10 cube into R31, which is would be 3i minus 6j at. Now if you do some algebraic calculation, you'll find out that F31 would be 21.34 into 10 to the power minus 3 I hit minus 7.11 into 10 to the power minus 3 j head. This is the F31. Same way, you can find out F21. So if you do in same way, you will find out the value of this F21. I just give you that calculation. I hope you can do by yourself. 3.55 into 10 to the minus 3 I hit plus 10.67 into 10 to the minus 3 j head. This would be the force. Now we can find out the resultant force. Now F net, which is actually summation of that, say F31 plus F21. If you add, you will find out that it would be 24.89 I hit plus 3.56 j head. So this is would be the resultant force on charge particle 1 due to charge 2 and 3. That would be your answer. Now you can do, so I find out the forces and Q1, right? Do the homework, net force on Q2 and Q3. That would be your homework. Homework. Find the net force on Q2 and Q3. By the same analogy, you can solve that one. That will be your homework. Yes. Do you have any more question, guys? So I can enter the Slack workspace. I even try to. Nazmul, why are you trying right now? Enter the Slack channel. Did you understand what I did over here? Do the right thing on the right time. Otherwise, life is going to be difficult. It's not too easy. So right now we start the two-dimensional. You have to find out the three-dimensional case, these charts. To try to cope up with that. Otherwise, guys, it will be very difficult. Very difficult. Unless you understand this thing, you cannot solve. Yes, any more question over here?
No, sir.
Did you understand what I talk about today?
Yes.
So fine, if you don't have any question, you can leave.
Sir.